Hey y'all, so we're going to go a little bit deeper now with our concepts of motion. All right, we've talked a little bit about distance, displacement, velocity, speed, acceleration, all that kind of stuff. Now what we want to do, remember the whole point of classical physics is that we want to be able to take information and use that information to predict what's going to happen later, right? Or to be able to try to figure out what happened before. Now we are making some assumptions. One of the assumptions that we're making is that the motion continues the same way before and after as what it's doing during the time that we measure. Now, there will be a lot of situations where that's not the case, and we actually have to stop using our information at a certain point. But for now, we'll go ahead and make the assumption that everything is constant as we go through. Now, I'm going to write up on the board 3 equations. There we go. So these 3 equations connect the things that we talked about last class. Now I'm going to go ahead and define each of those for you. So follow along with me. All right. So first we have x. Now x represents a distance. Now even though it's distance, we also often refer to it as a certain position from a 0 point. So when we say distance, it's a distance from some 0 location. So 20 means that I'm 20 meters, centimeters, whatever, away from my 0 point. So even though we call it distance, it can also be position. All right. Now, you'll notice that here, there's an x with a 0 as a subscript. The way that we say that is x naught. Now, x naught, what that means, naught is a word to describe 0. So this is an x sub 0. Any subscript is always a label. And the label of the 0 represents time 0. And so x naught is the position or the distance at time 0. And so that would then be our initial position or our initial distance. All right? Now, going forward, you probably recognize what a lot of these are. We've got a v, which represents velocity. Now, velocity is important, remember, because velocity is positive in one direction and negative in the other. That'll be pretty important as you start to work through these questions. So this is v naught, which will be the velocity at time 0. So that's the initial velocity. T, which of course is time. Now, the time specifically is the time between my initial position and my final position, right? The position at the end. You could, again, clarify that this is the final distance or final position. So the time is the time in between those 2 positions, all right? 1/2 a. A is the acceleration. Remember, acceleration can be positive or negative. And then we've got time, which again is that same t as before. Now you'll notice that most of these use the same variables, right? The only exception is we've got this one extra variable here, which is just the v. So if it has the 0, that's an initial position or initial velocity. If it doesn't, then it would be the final distance or position. And so this one, of course, you probably already figured out, is the final velocity. Everything else is the same. Initial velocity, acceleration, time, final velocity, the same as that v right there. It's just squared this time. Notice that that's an exponent. It's not a subscript, so it's not a label. That's a mathematical squared. Initial velocity, acceleration, and then final position minus initial position. All right? So really, we just have 1, 2, 3, 4, 5, 6 different variables. In each one, you'll notice that we have 4 or sometimes 5 different variables, all right? Which means that in each of these situations, I don't need one of them, right? And so based off of the information that you're given, you should be able to use these equations in a lot of different situations where we have what we call one-dimensional motion, where an object is moving forwards and backwards, or if an object is moving straight up and straight down. For now, we're just going to worry about one-dimensional motion, hopefully in a straight direction. We will look at that more as we get into some of the problems. All right? However, this is your introduction. At some point, we will go through the derivations of these. I'll show you where they come from. They actually all come from the stuff that we learned last class. You know, how we define displacement and velocity and acceleration in terms of each other. We can actually use those equations and some knowledge to be able to build these equations. For now, I just want you to get used to seeing them and practice using them, because you're going to see how to use these in an easy question all the way up to a quite difficult, challenging question at the very end. What's that? Oh, you want to know? This is a chocolate chip cookie. Why am I wearing a chocolate chip cookie? Why not? All right. All right. So that's all we've got right now. Go ahead and see if you can apply this. I should mention the one requirement here is that the acceleration is constant. You'll notice that there's not an initial and final acceleration. The reason why is because the acceleration in all these situations must be constant. If the acceleration is changing, then we cannot use these equations as is. And we're not going to actually deal with that in this class because that requires calculus. And we're not going to worry about calculus in this class. All right? Maybe in calculus class, you'll deal with this. If you've already been in calculus, you may have actually talked about how to get between position, velocity, and acceleration. But in this class, it's just algebraic, so we will make the assumption that acceleration is constant. Okay? Otherwise, everything should be pretty straightforward. Go ahead and try a few questions. I'll see you next time.